Bismillah ar-Rahman ar-Rahim. Assalamu alaikum wa rahmatullahi wa barakatuh. This is Hani Al-Ghamdi from the Electrical and Electronic Department at Jubail Industrial College. Today, inshallah, we are going to continue our lessons that related to the subject of electrical circuits 1. The previous 2 weeks, we have covered chapter 8 with 2 parts. Part 1, which is related to the source conversion, and part 2, that's related to mesh analysis method. Today, inshallah, we're going to cover the third part, which is the nodal analysis method. The nodal analysis method, it's another systematic method that can be applied to any circuit and to find the voltage of the nodes, and from the voltage, of course, we're going to find currents and powers. The question is that what we mean by the node. The node in general, it's any point, okay, that will receive 2 terminals to be connected to each other. So it's an interconnection point where 2 elements or more connecting each other. When I see this circuit here, let's say this diagram, okay, I can see this line connected with this line and with the third line here from one point here. So all of this line is calling one point and also another point here. So I have here two nodes, and what he need to explain in these 2 points, he need to tell you that with nodal analysis method you will start applying some steps, and by the end you will have some equations. Okay, how many equations I will have? He will say that the equation that you will have, it's 1 less than the total number of independent nodes. For example, in this figure here, I have 2 nodes. So my equation by the end, it will be 2 minus 1. So 1 less than the number of independent nodes. Let's assume this figure here. I have 4 nodes, as it's mentioned, 1, 2, 3, 4. So how many equations I will have in this circuit? I will have 3 equations for this 4 nodes. Okay, let's move on, and you are going to understand it more with real circuits. There are 4 steps need to be taken in consideration while you are dealing with the nodal analysis method. First of all, you have to study your circuit and to determine the number of nodes within that network. Okay guys, number 2, you have to pick a reference node. We will tell you how to pick a reference node. Step number 3, you will apply a Kerchief Current Law, which is KCL. So applying a Kerchief Current Law for all the nodes, so at each node except the reference node. And you have to assume something here. So we need to assume that all the unknown currents, what we mean by unknown currents, the currents for the resistors that we do not know its values. But if we have like a current source, this is called known currents because we know its value. So assume all the unknown currents are leaving the node. Step number 4, solve the resultant equations, and you will see what we mean by these steps here. So let's take a real example here. In example 8.1, he said apply nodal analysis to the network to determine I1 and I2. So let's study this circuit here. So step number 1, we said we need to determine how many nodes I have in this circuit, and we said that the node, it's the interconnection point between 2 terminals and more. When I check this terminal here of the current source, and this terminal from the resistor number 2, and this terminal from resistor number 3, I can see that these are connecting each other in 1 point. So I have 1 point here, or 1 node, let's say. Okay, come down here. So this terminal from the source, another terminal from the resistor number 2, and from the current source, so another node. So this is node number 2, let's say. Maybe you will say that this is a node. Yes, actually it's a node, but we do not need to consider it in this analysis method because it's already connected between two terminals, and these two terminals only a voltage source and a resistor. So as you can notice here, he stated we have to determine the node. So this is node number 1 and this is node number 2. Let's move on now. He said in step number 2, pick up a reference node. We will take this node here, which is down, as our reference node. Why? For two reasons. Usually the ground side here, which is the bottom of the circuit, it's taking more connections on it. I'm talking about its node. And also its value of the node voltage is 0 volt. So our reference here is 0 volt. So I will take this one. It will give me an easy way to solve this circuit with the nodal analysis method. So taking in your consideration, when you pick up a reference node, try to take it from the bottom side. I mean the nodal of the grounding here. So we have two nodes, which is 1 and 2. So we consider this one as a reference node. So the remaining node is what? Is node number 1. So the voltage here we name it as what? As V1. We mean by V1 the nodal voltage of node number 1. I'm not meaning here the voltage across resistor number 1. No. The voltage here we will name it as VR1. So the voltage drop of what? Of resistor number 1, or across resistor number 1. So we already determined the number of nodes. We picked up a reference node, which is from the bottom here, 0 volt, we said. And now we will apply a Kerchief Current Law. He said at each node except the reference. So we have only one node here. So we will apply the Kerchief Current Law for the node here. Let's read this sentence. We said that assume that all unknown currents, I mean the currents that will go or will move or will go through the resistors, are what? Are leaving the node. So this is our node here. So I will consider that the current is leaving the node. The current is leaving the node. But for the non-current, which is the source current here, we know its value already. So 1 ampere. So just keep it as it is. This is its direction going through the node. Let's go to apply the Kerchief Current Law here. So we know that the Kerchief Current Law is what? Is the summation of all currents equal to 0. Or as we remember, the currents entering is equal to the current leaving. Yes or not? You know that, if you remember, we said that all currents entering will equal all currents what? Leaving. So the summation of all current entering is equal to the summation of all current leaving. So we can write that. He did like that. It's actually what? It's actually the leaving current is what? Is I1 plus I2 is equal what? The entering current, which is the source current here, is entering the node. So it will be what? It will be the source I. So the leaving current, which is I1 plus I2, equal the entering current, which is I. Or you can take this one this side here. So you will have I1 plus I2 minus the I. Now just call your memory from the Ohm's law. I is equal what? V over R. This is Ohm's law, yes or not? So the voltage over the resistance. So when I come here and you will see I1, it's mean what? VR1, so the voltage across this resistor divided by its resistance, plus I2, so the voltage of the voltage across the voltage drop across resistor number 2 divided by its resistance, minus I, which is the source here, 1 ampere. Okay, there is one thing I need to mention here. When you're dealing with the nodal analysis method, okay, assume that the nodal voltage, which is V1 here, is the highest point. As you know, the voltage for across any element it's the voltage drop in that element, or in the other words, it's the potential difference between the highest and the lower point for that resistor or element. So we have here VR1. Look here, the voltage across resistor number 1 is what? Is the potential difference between V1 and the potential difference between V1 and the source, because it's located between these two, okay, points, which is V1 and the source voltage here. So the voltage across its terminals, it's the potential difference between V1 and what? And the source, minus the source. So V1 minus the voltage source E. Okay. And VR2 is the potential difference between its terminals again, which is positive and negative. So V1 minus what? Minus 0. So actually this one here, VR2 is equal what? Is equal V1 from this side, okay, minus V reference, which is 0. So it will be V1 minus 0, which is equal by the end V1. So the VR2, so the voltage across the terminals of R2 is what? Is V1 minus 0, which is V1. So the nodal voltage V1 as it's written here, minus I, so it's 1 ampere only. So let's check here now, just put your value. So V1, we do not know the nodal voltage, this is what we need to find. So V1 minus the source voltage here, which is 24, over R1, which is 6 ohm, plus again the nodal voltage V1 over 12, which is the resistor number 2, minus I, which is 1. This one here, they're having the same denominator, so I can split them into two parts. So V1 over 6 minus 24 over 6, and this just keep it as it is. So V1 over 12 minus 1. So take now a common factor, which is V1 here. So remaining here is what? 1 over 6 plus 1 over 12 minus 24 over 6, which is 4, minus 1. Minus 4 and minus 1, which is actually minus 5, and you can take it in the other side. I'm talking about these two. You can take it in the other side as what? As a positive 5. And if you use your calculator and adding 1 over 6 plus 1 over 12, you will get 0.25. So to find V1, just divide it, okay, 5 over the factor of V1 here, which is 0.25, so you will get 20 volts. So this is our nodal voltage. So the nodal voltage in this point here is equal what? Is equal 20 volt. Okay, we know that now the voltage here is 20 volt. So if I need to find the voltage across R2, which is VR2, it will be what? It will be V1 minus 0, which is the reference volt here. So 20 minus 0, it will be what? It will be 20. In case if we need to find the voltage across R1, which is VR1 here. We need to find this voltage, I mean. So it will be the voltage drop between its terminals. So the potential difference between positive and negative here. So it will be what? V1 minus the source voltage, which is 24. So V1 minus 24, which is 20 minus 24. Okay, guys? Okay. Before to continue, let's assume that this source here, okay, it's coming like that. So they flip the source, so negative and positive. So in this case, if you need to find VR1, you will say that, again, VR1 is the potential difference between the highest point, and we already assumed that the nodal voltage for any node, it's the highest point. Okay, guys, so it's the potential difference between the highest point, which is V1, minus what? Minus the lower point. And here, as you can notice, lower point is the source. But before, the positive was connected immediately to the R1. Now it's the negative connected to the R1. So it will be minus the source. So V1 minus the source. Or you can write like that, V1 plus the source voltage. I hope you understand it. So let's go back to our example here. So he asked us to find I1 and I2. So already we find the voltage of the node, which is 20 volt. So to find I1, we already know that I1 is equal V1 over V1, which is the nodal voltage, minus the source, which is the potential difference between its terminals, over the value of its resistance. So 20 minus 24 over 6, you will get by the end minus 0.06 ampere. For I2, we know that the voltage across resistor number 2, it's the highest point minus the lower point, which is the nodal voltage, V1 minus reference, which is 0 already, so it's V1, so 20 over its resistance, which is 12, it's equal 1.67 ampere. So again, this is our nodal analysis method. Just study your circuit, determine the nodes, pick up a reference node. After that, apply your Kerchief current law by assuming two things. One, the currents for the resistors are assuming to be leaving the node. Number two, when you're working with any node, so you have to consider that the value for this nodal voltage is the highest. Then you have to solve your equations. Let's see now another example here, which example 8.2. He said apply nodal analysis to the network in figure 8.51. When I check the circuit, you can notice here this is ground and this is ground. So it's nothing, guys. It's only like they are connecting each other to the ground, as it's clear here. Okay, so we need to determine how many nodes we have. So again, I have this node, which is the connection point between three elements, R1 from this side, R2 from this side, and the source current from this side. So let's say this is node number 1. And also I have another node here. So it's an interconnection point between R2I and R3. So this is my node number 2. And of course I have node number 3, which is at the bottom of the circuit here. That's connected to the ground by then. Okay, so this is step number 1 done. So we have to determine all the number of the nodes. So 1, 2, 3. Of course, the nodal voltage of node number 1, we name it as V1. Of course, you can pick another name. You can name it as Vx, and you can name, for example, V2 as Vy, whatever. And this one down here, it's our reference node. And again, the reference node, it's better to take it as take it for the node which is connected to the ground. Why? Because we will have the voltage is what here, 0 volt. So this is going to help us, okay, in ease the solution. So again, he explained the nodals 1 and 2 and the reference. Now what we need to do, guys, let's go and apply the Kerchief Current Law. So this is the node. So we will consider that the currents for the unknown parameters, which is I1 and I2, is what is leaving the node, while this one I will keep it as it is. So again, the Kerchief Current Law, we know it as what? That all the current entering should equal all the current leaving. So when I will check these three here, so I1 is leaving the node, so I will take it as I1 plus I2 is leaving the node even, so I2. Also the current source is leaving the node, so it will be what? Plus I. So I will add them, and for this node I'm not having any currents going through the node, I mean entering the node, so equal to 0. So let's take it one by one this time. I1 here is what? Again, I1 is what is the voltage over, so the voltage across resistor number 1 over its resistance. So what's the voltage? This is VR1, guys, okay? This is VR1, the voltage across resistor number 1. So the voltage across resistor number 1, or the voltage drop, is the potential difference between the highest point, and we are working in what? We are working at this node, so we have to take each node individually, guys. So we are working in node number 1 now. So it's the potential difference between the highest point, because we already said that when I'm working with a node, so I will consider its nodal voltage as the highest point. So the potential difference between the highest point minus what? The lower point, which is E. So from here to here. So this is the voltage drop across resistor number 1 over its resistor, which is R1. Done. For I2, this is I2 here. So I have V1 here, but do not forget also I have V2 here. Okay, so I'm working with this node. So my highest point here is what? Is V1. So again, I2 is what? Is equal to what? The voltage drop across R2 over its resistance. Okay, what is the voltage drop across R2 here? It's the potential difference between its terminals, or between the highest point, which is V1, and what? And lower point, which is V2. So V1 minus V2. So again, here rewrite it now with the full information. So I1, as we said, V1 minus E over R1 plus I2, which is V1 minus V2 over R2, and plus a current source, which is I. You can put the numbers immediately here, or you can just simplify it. Okay, then put your numbers. What he did here, again, I have a common denominators, so I can split it into parts. So he take it V1 over R1 minus E over R1, then plus V1 over R2 minus V2 over R2 plus I. So take a common factor here. I have V1 and I have here is V1. So remaining is 1 over R1 plus 1 over R2. Then he take this one here down. He took out V2, so minus V2 remaining 1 over R2 equal to what? He take this one to the other side. It was positive, so it will be now negative. And taking this one again to the other side. Why taking these values to the other side? Because it's non-values. Because we know here the source, we know the value of R1, we know the value of the current source, so we can take it to the other side. So it will be -1 plus E over R1. So now just put your numbers. We do not know V1, we do not know V2. So, but we know R1, so 8 ohm. We know R2, 4 ohm. We know R2 here again, 4 ohm. Equal what? Minus current source, which is -2, plus E over R1, which is 64 over 8. 64 over 8, which is 8. So, -2, positive 8. The remaining is what? Is 6. Okay, you do not need to put the units here. No need. It's already clear. So remaining what? Like that one. So this is my equation number 1. Equation number 1 that relates to the node number 1, which is V1. Let's go to the node number 2 now and apply the Kerchief current law. So again, simple, it's easy. But this time I will focusing in V2. So we're assuming that the current is leaving the node, as you can notice, I2 and I3. So what is the Kerchief current law said? It said the current leaving the node I2 plus I3 is equal to what? The current that entering the node. So as you can notice, the source current here is entering the node. Okay, so I2 plus I3 equal the source current itself. Or you can take this one inside here and you will write it like this. Do whatever you want. Because by the end, all the summation of the currents entering and leaving should equal to 0. So let's take it one by one now. or just solve it immediately. Look here. So this is I. Keep it as it is. Equal to what? He said I2. So I2 is what? Is the voltage across R2 divided by what? By its resistance. So this is the current. Again, do not forget that we have here what? The node number 1. So I'm working now with what? With node number 2. So I will assume that the nodal voltage here is the highest point. So the voltage across R2, it's the potential difference between the highest point, which is V2, minus what? The lower point, which is V1, over its resistance, which is R2. Then I have R3 here. When I check R3, so I need the voltage difference between its terminals, between positive and negative here. The voltage drop, I mean. So it will be what? The potential difference between the highest point, which is V2, minus what? Minus the lower point. And the lower point here is what? Is V reference. And the V reference is equal to what? Is equal to 0 volt. So no need to write it. So immediately it's V2 minus 0. So V2. Again, they having the same denominator. So I can split them into two parts. So V2 over R2 minus, make sure that you write the right or the correct, let's say, signs, and V1 over R2 plus V2 over R3. Again, you have here V2, you have V2, so you can take a common factor here, and the remaining is 1 over R2 plus 1 over R3, then minus, you can take the V1 out, and the remaining is 1 over R2. It's equal to the current source, which is I. So just put your numbers, and again, you do not need to put the units in, inside the steps. It will be enough for the final answer. So it will be 1 over R2, which is 4, 1 over R3, which is 10, 1 over R2, which is 4, and the current source is what? Is 2 ampere. Just make your answer in a good arrangement. So take V1 first, so minus V1 over 4 ohm. Then take this one, so plus V2, and its coefficient or factor equal to 2 amperes. So I will have here equation number 2. Now I will have two equations, which is we're already having equation number 1, and this time we have equation number 2. So equation number 1 from node 1, equation number 2 from node 2. Now I need to solve these two equations. This is our equations 1 and 2, to find the value of the nodal voltages V1 and V2. Use your calculator, add 1 over 8 plus 1 over 4, you will get 0.375, and again 1 over 4, which is 0.25. Don't forget to take the right signs, minus, so just keep it as minus. So 1 over 4, it's again 0.25. Here 1 over 4 plus 1 over 10, which is 0.35 V2. Okay, I will go back to the side down here, but let's now think how to solve these two equations. We have different methods. I will use two methods today. So we can solve these two equations by a method called substitution method. What do we mean by substitution method? The substitution method, you will start, okay, by cancelling one of the unknown parameters. So you can cancel V1 or V2. So cancel one, keep the other, find its value, then substitute its value in one of these two equations. Let's go through it. So again, this is our equations. Okay, you can do many things here, okay, if you need to cancel, but take it as a formula now, it's better. Take the second equation and multiply it by what? For example, now our goal is to cancel V2. Okay, so I will keep V1 and I will cancel V2. So to cancel V2, I should let their coefficients, I mean these numbers, these two numbers, having the same numbers but with different signs, like this one, minus and positive. So it's already here, it's minus and positive, so I can cancel them. For example, if this one 2 and this one is 2, so minus 2, positive 10 will be 0, so it will be cancelled. So I need to make them unified factors here. So take equation number 2 and multiply it. Multiply the whole equation by what? By 0.25, which is this number, divided by 0.35, which is the factors that I need to cancel it, okay, parts, which is V2 here. So 0.25 over 0.35, which is equal 0.174. Now multiply 0.174 into 0.25, of course with minus, you will get this answer. Multiply 0.174 into positive 0.35, you will get this answer, 0.25, and multiply 0.174 into 2, which is 1.428. So don't forget to multiply the whole equation. If you can notice here, I have the same number, 0.25 and 0.25. This is positive, sorry, this is negative and this is positive, so it can be cancelled, yes or not? Because minus 0.25 V2 plus 0.25 V2, it's what? It's 0, so I can cancel it. Of course, don't forget I will add here the summation between the two equations. Before to continue, I need to mention something here. Let's assume the value here is with a minus sign, not with the positive. So you have to multiply by what? By minus by the end. Why? Because when I multiply minus with the minus, it will become positive and it will be cancelled. But minus with minus, you cannot cancel them, you can add them. If you have minus 0.25 and minus 0.25, it will be what? Minus 5, yes or not? Minus 0.5. Okay, done. So we cancelled V2, so remaining is what? The values of V1. So just add them. 0.375 minus 0.178, it will be 0.95 V1. Again, add 6 plus, because we did not, and this is also plus here, so 6 plus 1.428, it will be 7.428, and just divide this number by the factor of V1, you will get V1 equal what? 37.7, which is actually 37.882. Now what we need to do, guys, we already found V1, so we need to find V2. We have two equations here, so take the value of V1 and substitute it in any equation, and you will get by the end what? V2. So he said that let's substitute V1, because it's known now, in equation number 1. So this is our equation number 1. Take the value of V1, which is 37.82. Multiply these two numbers, 0.375 into 37.82, which is the V1, the nodal voltage of node number 1, minus 0.25 V2. So the resultant value of this multiplication is 14.183 minus 0.25 V2 equals 6. What he did, he took this value to the other side, so remaining is 0.25 V2 equals 6 minus 14.183. Why minus? Because it was positive here and it should be go to the other side with a different sign. So to find V2, just divide this number by the factor of V2, which is minus 8.183 over minus 0.25. So minus divided by minus 2 will be positive, and 8.183 divided by 0.25, which is 32.73. So if I go back, I got the same number, so 32.73. So this is one method to find or to solve these equations. It's called substitution method. Do we have another method? Yes. We have another method. It's called matrix method. So again, this is our equations 1 and 2. You have to create 3 matrices, 1, 2, 3. In equation in matrix number 2, just put your unknown parameters that you need to find, the which is V1 and V2. Okay, for the third matrix here, okay, put the constant number from the equation number 1, the constant number, which is what? 6, and the second constant number from equation number 2 is 2. Consider the first row for all the matrices corresponding to what? To V1. Corresponding to equation number 1. And the second row here corresponding to what? To equation number 2. The first row, I'm talking about the first matrix, guys, now, okay? So the first matrix here, we have to consider that, or we have to know that, okay, the first row corresponds to equation number 1, okay, while the second row here corresponds to equation number 2. Okay, the first row in this matrix, the first column, it corresponds to V1, okay, and the second row it corresponds to V2. So let's look now. So this is equation number 1, and here is V1. So this is correspond to 0.375, which is from equation 1 and related to V1. And here what is minus 0.25, and in this column we say this is corresponding to what? To V2. Again, go to equation number 2 here. So minus 0.25, which is related to V1, and 0.35 with positive, of course, that correspond to V2. So these are our matrices here, 1 and 2 and 3. First of all, you have to find something called delta. Delta, just take the first matrix only, ignore the others. Okay. put it between absolute like that here. How to find it? This direction here, it's called main diagonal, and this direction here, it's called what? Off diagonal. So multiply the main diagonal numbers, or let's say that multiply all the numbers that's coming in the main diagonal, which is coming here, as you can notice, with the blue color. So 0.375 multiply 0.35 and subtract it, okay, from the resulting of what? Of the multiplication of the off diagonal numbers, which is minus 0.25 multiply minus 0.25. That's coming with the green color. So find the resultant of this one and just subtract it from the resultant of this one. So 0.0685. So this is the delta. Please take the signs as it is. So you have to make sure this is a minus here, because you have to subtract the resulting of the multiplication from the main diagonal from what? From the off diagonal. Minus, so you have to take it minus. Minus, you have to take it minus. Like that. So this is our delta here. Now let's go and having our V1. He said that V1 is equal what? Is equal delta V1 over delta. For the delta we know the values, which is 0.685. Yes or not? Done. Let's now find delta V1. The delta V1, go to the first matrix here. You need to find V1, yes or not? So just remove this one here and keep this one. So minus 0.25, 0.35. And this constant number, take it from here and put it, okay, or replace it by the columns that correspond to the V1. That's all. Then do again like what we have done before. So multiply this diagonal by the off diagonal. So multiply the diagonal numbers and subtract it, sorry, from the off diagonal numbers. So 6 multiply 35 minus 0.25. It's good to put it between brackets. So we're gonna to help you to distinguish for the signs. I mean the negative and positive polarities here. Multiply by what? By 2. So the answer by the end it will become 2.6. So divided by the delta. So delta V1 is 2.6 and delta, which is 0.0685. The answer is what? Is 37.9. Okay, which is approximately the same answer that we have found from the previous method. V2 same. Delta V2 over delta. Again, we know the delta. For the delta V2 this time, no. You have to cancel this, which is correspond to V2, and replace it with what? With 6, 2, which is the constant from here. And just keep the first column as it is, from the first matrix, I mean. So 0.37, 5, and here this one minus 0.25. So multiply the diagonal numbers, subtract it from the multiplication of what? Of diagonal number. You will get 2.25, and this is our delta. Divide it. Your answer is 32.8. So when I go back here, of course, it's approximately the same values. So you can apply any method that you like. So we already have done the nodal voltages and we have found its values, or their values. In case if you need to find, for example, IR1, which is the current coming here, we know that IR1, as we already described it in the steps of the equation, it's he said what? E minus V1, yes or not? Why this time he said E, and we said that it's okay V1 minus E in the previous steps, because we considered and we assumed that the highest point is what? Is the node voltage. But now I know the voltage of V1, how much? It's 37.82, and the source voltage is what? Is 64. So this one, okay, is greater than this one. So I can take it as E minus V1, and the value it will be 3.7 ampere. If you take it, okay, like V1 minus here, if you take it V1 minus E, you will get the same answer but with negative sign. Okay, and we prefer always our answer to be what? To be positive, because the positive, it's the actual values. Again, the same thing here and here. Okay, let's check the last example here, which is example 8.2. Again, determine the nodal voltages for the network in figure 8.55. So again, guys, study your circuit. First of all, determine all the nodes. So this is node number 1. It's clear here, and the node would mean that any line or any point that receive many connection on it. Okay, so this is 1. Again, this is 2, and I have down here what? Number 3, and we'll pick this one as our reference because we said it's better to take the bottom, okay, node which is related to the ground as a reference. And usually, guys, the reference node, okay, it's coming with the maximum number of connections. Like here, I have 1, 2, 3, 4 elements connected to this node. So again, I will name it as V1 for node 1, the voltage here, V2 for node 2, and this is our reference. We know it's 0 volt. Okay, so let's work with each node individually. I will work with V1 here, but of course I have V2 here, do not forget it. Okay, shabab, but I will consider the node number 1 only, and we will assume it as a highest point as we agreed. Just I will show you how to write the equations, and you can solve it by any methods that you have already done for the previous example. So when I check it here, we need to assume that again the current is leaving the node. I'm talking about node number 1 now. So the current is leaving the node. So what we will need to do, Kerchief Current Law, okay, it said what? All the currents entering equal all the current leavings. So the current entering here is what? It's 4. Focus here. Okay, so 4 ampere is entering the nodes, and the current that leaving the node is what? Is I1 and I3. Okay, and you can take this one inside here as he done it here. Okay, now what you need to do, guys, just find the current. So here is 4 ampere, we know it, the source current itself. For I1 here, shabab, so again, it's what? It's its voltage divided by its resistance. We know its resistance, which is R1, but its voltage what? The VR1 here, VR1, it's the potential difference between the highest point, which is V1, minus the lower point, which is 0 volt, so it will be V1. Okay, then a plus I3. This is I3, which is R3, I know it, but with the voltage here, it will be what? The potential difference between the highest point, which is V1. Why V1 the highest point? Because I'm working with what? With node 1, which is V1 here, okay? Minus the lower point, which is V2. Why? Because here V1 and here is V2, and R3 is located between these two nodes, from here and from here. So the voltage drop is what? V1 minus V2. And just you can put the values, R1 which is 2 ohm, R3 which is 12 ohm. Again, he took 4 ampere and put it here. V1, I will take it as a common factor. So remaining 1 over 2 plus 1 over 12. And here is I will take V2 out. Remaining minus, or say yes, minus V2, which is 1 over multiplying by 1 over 12. So this is equation number 1. Let's go to node number 2. So this time I will consider this one as the highest point because I'm working in this node. But again, do not forget that I have V1 here. Why I'm saying that? Because, for example, here we're assuming the currents going out of the nodes, yes? And for R3, for example, it's located between the two nodes here. So this will gonna help me to find its voltage. So again, when I check it, I can notice that all the parameters that connected to this node is leaving the node. So I3 plus I2 plus 2 ampere equal to 0 because I do not have any currents that entering the node. I3 again, it's located between the two nodes, so it will be its voltage divided by its resistance. Its voltage is the voltage across R3 itself, which is the potential difference between node number 2, because it's considered as the highest now because I'm working on it, minus what? Minus V1 over R3, plus I2, again this is I2 from here to here. So I need to know the voltage across its terminals, which is V2 minus 0 volt, because we know this is 0 volt down here. So it will be V2 plus 2 ampere. Just put your numbers and create your equations. So now I have two equations, equation 1 and 2. Okay, use your calculator better, guys. Add these numbers and find it with the 0 point something like that. Okay, do not make it as a fraction. Then you can apply any method, substitution method or the matrix method. Please try it in your home, and you will have by the end the values is what? V1 as 6 volt, positive 6 volt, and V2 negative 6 volt. Okay, let's go back here. He said find, for example, if he asks you to find I3. So I3 here, I can find it, okay, from node number 1 or from node number 2. Okay, for example here, I3 is what? I3 is V2 minus V1 equal R3. This is from node number 2. And from node number 1, I can say V1 minus V2 over R3. So you will get the same answer but with different sign. But it's better to find it with a positive. How to find it with a positive answer? I mean, since the V1 is greater than V2, so it will be what? V1 minus V2. So this is the voltage across, or let's say the actual voltage across R3. And you can find, of course, I3 and I1, which is related to the resistor number 1, and IR2. You have two problems here, guys. Problem number 1 with two parts, and of course another problem. Please go through them and try to do it. Practice yourself. This is what we have for this lecture. I hope you understand all its parts, and you are welcome to ask us, guys, through the email or the virtual classes with other teachers. See you.